Next, we are going to look at actually pairs of random variables. This can be generalized to more than 2 random variables, but I'm not going to go into that. I'm just going to give you the case with just 2 random variables, and we will define the joint distribution of 2 random variables x and y in this way. Okay, so the PMF, the joint PMF, p sub xy ij equals the probability, the joint probability of the joint event, x equals I and y equals j. So this is essentially an intersection event. X equals I, and at the same time, y equals j. Now from this, we can obtain the marginal distributions. Marginal means the distribution of x just by itself and y by itself. And we can obtain these by adding the joint distribution over all possible values that y can take here. So the marginal distribution of x at k can be obtained by adding up this joint distribution where x takes the value k, this one, and you just put in all possible values of y and add them up, and you get this probability. Similarly, if you fix the value of y to k and add all probabilities with all possible outcomes of x, what you obtain is the probability of y at value k. So these we call the marginal distributions, the marginal distribution of x, the marginal distribution of y. And the concept of correlation is defined between 2 random variables x and y through this formula. And essentially the correlation of x and y is equal to the expected value of the product x times y. And we can compute this with the double sum through I and j, where x takes values I and y takes the values j, I times j times their joint probability. So this is again a weighted sum of the function x multiplied by y. So the correlation is a measure of how 2 random variables resemble each other. And similarly, we define the covariance in this way. The covariance of x and y is defined as the expected value of x minus its mean multiplied by y minus its mean. And if you expand this expression, you get correlation minus the product of the means. And this is the covariance between x and y. And based on covariance, we define the correlation coefficient between random variables x and y as the ratio of the covariance to the product of the standard deviations of x and y. The correlation coefficient is a parameter between -1 and +1, and it actually represents the relationship between the 2 random variables. Essentially, if rho equals 0, we say that random variables x and y are uncorrelated. This doesn't say they are independent, but it says they are uncorrelated. So from one, you cannot actually estimate the other. Essentially, it's what it means. And the correlation becomes stronger as the parameter rho, the correlation coefficient, becomes closer to 1 in magnitude. So if you have, for instance, random variable x and random variable y as a linear function of x, this is the most strongly correlated case where one is a linear function of the other, in which case their correlation coefficient will be equal to either plus or -1. If a is a positive number, their correlation coefficient will be +1, because, well, when one of them increases, the other will also increase. When one of them decreases, the other will also decrease. There is a 1-to-1 correspondence. But if a is negative, then the correlation coefficient will be -1. So this case is the extreme correlation case. And the other extreme is rho equals 0, in which case we say they are uncorrelated. As I said, this is not independence, this is something else. So what is independence? We talked about independence in the context of events. And there, if you remember, we defined independence in terms of conditional probabilities. If probability of A is equal to probability of A given B, which means the event B has no effect on event A, we say that they are independent. And actually, the definition is the same with random variables, but since we didn't study conditional distributions, I'm not going to give that definition. For only two random variables, we will say that random variables x and y are independent if for all ij, their joint distribution at ij is equal to the marginal distribution of x evaluated at I times the marginal distribution of y evaluated at j. So if you can separate the distribution in a product form, then these two random variables are independent. Now be careful, as I said, let me repeat this. The definition is in fact comes from conditional distributions. In fact, we would say the conditional distribution of x given y, let's say value of y, if this is equal to the marginal distribution of x at k, then we say that they are independent. But this implies this, and if it's just two random variables, they actually imply each other. However, if you have more than two random variables, remember my quotient in independent events, the product form by itself does not guarantee independence. Here, that is the same. This is the pair of random variables is a special case. If you have just two, x and y, the product form guarantees independence. But if you have more than two random variables, x, y, z, for instance, then the product form may not guarantee independence. So be careful about this. If x and y are independent, the correlation turns out to be equal to the product of the expected values, because the joint density, the joint distribution, because this product you see is equal to the joint PMF. Since this is separable, the correlation turns out to be equal to the product of the means, which turns out, which entails that the covariance becomes zero, because if you remember, the covariance of x and y equals the correlation minus product of the means. And if the correlation equals the product of the means, this is essentially zero, which also means the correlation coefficient is also zero. Now, what does this tell us? Independent random variables are always uncorrelated, because this is the case. If you have independence, right, then correlation equals the product of the means. This is not, by the way, this is not a general rule. So in general, correlation is not equal to the product of the means. This is a mistake very frequently done. Okay, so the correlation does not in general equal the product of the means. But if x and y are independent, they are equal, which means the correlation coefficient is zero. Therefore, independent random variables are always uncorrelated, but it's not the other way around. Uncorrelated random variables may or may not be independent.